Welcome back to Calculus 1. In this lecture, we're going to revisit a topic we introduced earlier, derivatives as rates of change. Now that we have access to differentiation rules, we'll be able to look at some interesting questions since calculating derivatives will now be considerably easier than using the limit definition. All right, so let's think back to this question, which we brought up several times. What is a derivative? Now, there's several answers depending on the kind of the idea that we're learning about. We have three answers here. We can say a derivative is a slope of a tangent line. That was our first way to think of a derivative. Derivatives are also instantaneous rates of change. And depending on the context, if we want a more mathematical understanding, we can say derivatives are limits. Now, for this lecture, we're going to build off this second idea, which we did see earlier thinking about position and velocity, velocity being the instantaneous rate of change of something. And we're going to go into deeper with that now that we have access to differentiation rules and easier ways to calculate derivatives. All right, so let's just review some notation from when we first introduced this. Let's say we have a function y equals f of x. And the first thing we might be interested in, kind of going back to our introduction to calculus, when we first started by finding the slope of a secant line, is we need an average rate of change. So here we have the average rate of change of the function f over the interval of x values from a to b. And this is pretty much your basic slope formula. The change in y values divided by the change in x values. The only change here is notation. y2, we're going to write it as f of b. y1, we're going to write it as f of a. So recall function values are y values. This is just your slope formula from algebra in different notation. All right, so this is a rate of change over an interval. Calculus comes in when we try to define an instantaneous rate of change for a function. So what we need to do is make that interval shorter. This was our approach with finding the slope of a tangent line where we introduced limits. So the idea was we saw a derivative, f prime of a, which we can define it and write it as the limit as delta x approaches 0. So that's above there in the average rate of change. It's the limit as the width between those x values becomes really small, but it's the limit of your average rate of change, delta y over delta x. So delta y over delta x above is an average rate of change. The limit of delta y over delta x as delta x approaches 0, that is a derivative, what we interpret as an instantaneous rate of change of that function. All right, just make sure you're comfortable with the notation. We're going to be referring back to this at several points. Notice down there in red, we're using Leibniz notation, differential notation, for the derivative, which we're going to use that predominantly throughout this lecture, since rates of change, something per something, we kind of think of it as a fraction. This notation, dy over dx, mostly resembles kind of a rate of change rather than f prime of a. Okay, now with that, let's get to the main idea. And this is kind of why I'll say calculus and mathematics is so useful. It's that it's very general. So let's just say we have a function, f of x. We won't give any physical interpretation to what that function is. And then the idea is the derivative that represents that function's instantaneous rate of change with respect to x. So the idea, a derivative is an instantaneous rate of change. Now, how you're going to apply this to your science and engineering courses is giving an interpretation to the function. The function could represent many different physical quantities. And when we give an interpretation to that function, then the derivative of that function would be that quantity's rate of change. All right, let's take a look at several examples on that just to let that sink in. Let's go back to the first place that we would have introduced derivatives as rates of change. So let's say our function, let's write it as s of t. This was our notation for position of an object as a function of time. And if we define the instantaneous rate of change of position with respect to time as ds over dt, a rate of change of position, that is exactly what velocity represents. So the thought is if s of t represents the position of an object, the derivative of that function, the derivative of position, gives you the rate of change of position, which is what we call velocity. So we'll be sticking with this notation. S of t denotes position as a function of time, and we can write ds over dt, the velocity. We're going to use that and write that as v as a function of t. All right, let's take a look at a different example, giving a different interpretation to our function. So let's say we have p as a function of t, representing population as a function of time. Now, this could be like a population of like a city, could be a population of a bacteria culture, could be anything. But if p of t represents the population at a certain time, the derivative dp over dt, which we could write as p prime, that represents the instantaneous rate of change of population. So not what the population is, but how fast it's changing. All right, let's take a look at one last example, just to tie this into maybe like your physics and chemistry courses. Let's say we have a function p that represents pressure, and maybe the pressure changes with volume. So we'll say P denotes the pressure of an ideal gas, and then V denotes its volume. You might not be familiar with down there the ideal gas law, but you might have encountered that in a physics or chemistry course. PV equals nRT, where P is the pressure, V is the volume, and T denotes the temperature for that ideal gas. Okay, now the only thing we're going to need for our calculus course is the idea that if P represents the pressure as a function of volume, dP over dV, or in other words, the derivative of pressure with respect to volume, that now represents the instantaneous rate of change of pressure. All right, so just take a few seconds, let that sink in. Whatever interpretation we give to the function, the derivative would then represent the instantaneous rate of change of that function. So derivatives are instantaneous rates of change. It's left to your science and engineering courses to give a physical interpretation to what that function represents. All right, when you're ready, let's take a look at a short example one. So let's take a look at an example here where we're given population as a function of time. So we're given P as a function of T. And it's worth pointing out, notice in the kind of the very beginning, the statement of the example, the units for population represent thousands of people. So if we plug in a value for time and we get, for instance, maybe the output value is 10, that would represent not 10 people, but 10,000 people. So the units here are thousands of people for the population, and then the units for time are years. Now, what the question wants is for you to find not what the population is after a year, but what is the rate of change of the town's population after 1 year. The thought is what we were covering a few minutes ago, the derivative of that function would represent the instantaneous rate of change. All right, so give this one an attempt. Calculating the derivative here of P of T just requires the basic power rule, and we'll check in maybe 1 or 2 minutes. All right, welcome back. So the population here is given as P of t minus a quarter t to the fourth plus t squared plus 4t plus 1. Since the question wants us to find the rate of change of population, we're going to calculate a derivative. Now, just make sure you're comfortable with the notation. Previously, we were expressing and writing derivatives using the prime notation. So we can say p prime of t, that represents the derivative of the population function. For this lecture, we're going to switch to differential or Leibniz notation for the derivatives. And instead of writing it as p prime of t, we're going to write it as dp over dt, since that looks more like a rate of change, something per something. All right, so for that function, it's pretty straightforward to calculate the derivative. We don't need product or quotient rule, just basic power rule. So we should get our derivative as negative t cubed plus 2t plus 4. There's some work right below here just to make sure you can calculate the derivative of each term individually. And we're pretty much done at this point. The question, though, wants not what the derivative is by itself, but it wants a rate of change at a particular time value. So we're going to take our derivative, p prime, or dp over dt, and now we're going to evaluate it at 1 year. So we're just going to plug in t equals 1 to the derivative. And if we do that, we should get that, an output value for that rate of change as 5. Now just make sure you're comfortable with what the units for this would be. Recall the units for population were thousands of people. So our units here for the rate of change, the population has units of thousands of people. Time is in units of years. The output value, 5, that we get, the units for that would be 5,000 people per year. Or in other words, the population is changing at that time, 1 year, at a rate of 5,000 people per year. All right, so now the work is actually very minimal. It's just now the conceptual interpretation of a derivative as an instantaneous rate of change. Now, your science courses are probably going to be more particular about units, but let's just take a look at the advantages of differential or Leibniz notation. dp over dt, while it is not a fraction, recall derivatives are limits, you can kind of think of it as being 1, at least for getting the units correct. So in the numerator, dp, p, the population, has units of thousands of people. And then in the denominator, dt, or t, that has units of years. So that's why we get here our units as 5, but thousands of people per year. All right, so that's it for example 1. Before we get to example 2, let's go back to just be clear on some physical quantities, position, velocity, and acceleration, just to get you ready for example 2. It was a little cumbersome at the time to answer questions using position, velocity, and acceleration with the limit definition of the derivative. But now, with access to differentiation rules, these questions will be considerably simpler. All right, so the central idea that we kind of addressed earlier, very briefly, is if the position of an object, so for one-dimensional motion, we denote that by s of t, the velocity is s prime, a derivative, and then the acceleration, which is itself a rate of change, but of velocity, the acceleration, we can write it as v prime, the derivative of velocity, but since velocity is itself a derivative, we can write the acceleration as the second derivative of position. All right, so that's kind of important for our course. S of t denotes the position, s prime denotes the velocity, and s double prime, a second derivative, denotes the acceleration. All right, now we're not going to get into detail like you would in a physics course, but velocity has a how fast and a direction to it. Speed, which we can define it to be the magnitude of velocity, for us, with one-dimensional motion, the sign is going to denote the direction. So positive would be traveling to the right or pointing in the right to the right. Negative would be traveling to the left or pointing to the left. So for speed, we're just taking the absolute value. In your physics courses, maybe later in Calc 3, when you introduce vectors, you'll revisit this. All right, so for us, for one-dimensional motion, we're just basically considering an object moving along a straight line, just moving left and right, back and forth. And the position can change over time. So let's say at time equals 1, the object is right here. 1 second later, it moves a little further to the right. 1 second after that, a little further to the right again. But 1 second later, notice it suddenly moved very quickly to the left. So your position can change. So can your velocity, your direction of travel. So let's just be clear on some of these quantities. Since we are not in a physics course, let's just get the kind of bare minimum that we need to answer typical questions in calculus related to position, velocity, and acceleration. All right, so first, when the velocity is positive, that represents the object moving to the right. And when the velocity is negative, that means the object is moving to the left. Notice here, it is the sign of velocity that determines the direction that you're traveling. All right, similarly, the acceleration has a direction. So when the acceleration is positive, we're accelerating to the right, or our acceleration vector is pointing to the right. And when our acceleration is negative, the acceleration is pointing to the left. All right, now some of the questions that we'll be getting to ask us to find all times for which an object is speeding up or times for which an object is slowing down. Now, again, we are not in a physics course, but what we need to be clear on for Calculus 1 is the direction for velocity and acceleration is given by the sign, positive or negative. Positive is pointing to the right, negative is pointing to the left. Now, in your physics course, which we're going to just briefly review here, or kind of learn for the first time, when an object's speeding up, that's when the velocity and acceleration are in the same direction. For our questions, that means the velocity and acceleration, if they have the same direction, they have the same sign. They're either both positive or they're both negative. When an object is slowing down, that's when the velocity and acceleration are in opposite directions. For us, that would be when the velocity and acceleration have opposite signs. One of those quantities is positive, the other is negative. That would then represent times for which the object is slowing down. Now, if needed, pause, copy this down, that way you can have it in front of you. The next example that we look at, example 2, goes into detail about answering questions dealing with position, velocity, acceleration, direction of travel, and then times for which the object is speeding up or slowing down. I'll pause. When you're ready, we'll move on to example 2. All right, if you're ready, let's take a look at example 2. There's a lot of parts here, 4 parts. Most of it is just kind of dealing with determining the signs within parts C and D, which we're going to take our time with, since that'll be something that kind of pops up later through the course. So right now, this example, example 2, deals with position, velocity, acceleration. So a interpretation of derivatives as rates of change. But in us answering part C and D with creating what we're going to call sign charts, we'll be using those throughout the course. All right, so let me pause if you just want to copy this down just to digest the problem. All right, and the problem starts giving us the position of an object moving along a coordinate axis, so it's just moving in a straight line. And it's given the position S of t as t cubed minus 15t squared plus 48t plus 1. And that's basically going to be valid for all time values from 0 on. All right, now I'd like you to make an attempt at part A. Part A is pretty much the only place where calculus is used. Part A is asking to find velocity and acceleration, which are the first and second derivatives of position. So give yourself an attempt at part A, pause the video, give yourself maybe 2 minutes. Given the position function S of t, calculate the first and second derivatives. That would represent physically the velocity and acceleration. We'll check in maybe 2 minutes. All right, let's go through part A. Part A is really the only place calculus is used within this, this question, this 4-part example. All right, so I'm just writing the position function S of t. And notice here, the derivative is very straightforward to calculate using the power rule. All right, so our velocity, v of t, which is s prime, the first derivative of position, that would come out to 3t squared minus 30t plus 48. And if we differentiate that to get the second derivative, s double prime, physically, that's what we think of as being acceleration. So we get the velocity, v of t, and acceleration, a of t, for minimal effort. Okay, now that pretty much does it for part A. Earlier, when we were calculating derivatives, a lot of examples, we simplified the derivatives after we calculated them. Now take a look at v of t and a of t. See if you can simplify those in any way. Pause the video and maybe give yourself 30 seconds to see if you can simplify v of t and a of t. I'm intentionally being vague about how you would simplify them. See what you can do. We'll check in 30 seconds. All right, now how can you simplify v of t and a of t? Well, the only thing we can do, there's no like terms to combine, but we can factor them. And factoring v of t and a of t will make all the other parts, b through d, so much easier. So hopefully that goes pretty well for you to factor. Shouldn't be too bad. Now we can move on to part B, which will be pretty simple to answer. Part B is asking at what time or times is the object at rest. Now, if you want, pause to give an attempt at this. When an object is at rest, that's when the velocity equals 0. So set up an equation, set the velocity equal to 0, and see if you can solve that for t. We'll check in about a minute. All right, now the work should be pretty simple since we already, within part A, factored the velocity function. So we take our velocity right above, we're going to set it equal to 0, and then we solve that, and the work's already done since we already simplified that derivative by factoring. That's a very simple quadratic equation in factored form. If we set each factor to 0, we should get two values for time at which the object is at rest. T equals 2 and t equals 8. So part A and B go pretty quickly. Now parts C and D, these are the new parts. Part C is asking the direction in which the object is traveling. So find times when it's traveling to the right, and then find times which is when it's traveling to the left. Part D is asking when the object is speeding up and when it's slowing down. Both parts C and D deal with directions for velocity and acceleration. For us, for one-dimensional motion, direction is indicated just by a positive or negative sign. All of our work for parts C and D are going to come from using what I'll call sign charts. Now, just so you see it before we move on, notice what we know from part B. We know at t equals 2 and t equals 8, the velocity equals 0. Now, what would it mean then for all other times? Those are the only two times for which the velocity equals 0. At all other times, the velocity should be either positive or it should be negative. And that's going to be how we use a sign chart. We're first going to determine where that quantity equals 0. And then at all other values for time here, that quantity would be positive or negative. So just make sure you reference here, we have two values for which the velocity is 0, t equals 2 and t equals 8. Let's go ahead to the next page to create the sign chart for velocity. All right, so I have at the top there our factored version for the velocity function. Just to briefly review, the object will be moving to the right whenever the velocity is positive, and the object's going to be moving to the left when the velocity is negative. All right, we're going to determine and answer those questions, all intervals or values for time when it's traveling to the right or left, by using a sign chart for the velocity. All right, and what we first use are the values of time for which the velocity equals 0. We found those within part B. Those were t equals 2 and t equals 8. So we're going to basically split our interval of time from 0 to infinity. We're going to split it into 3 intervals between 2 and 8. So we get 3 intervals, 0 to 2, 2 to 8, and then 8 to infinity. Now, how we're going to determine the sign for velocity on each interval. Remember, we're just trying to determine if the velocity is positive or negative. That'll tell us when the object's traveling to the right or left. We're going to pick a test point, just any value for time within those 3 intervals. And then we're going to plug them into the velocity. And that will tell us at each of those test points, and also correspondingly on those intervals, if the velocity is positive or if the velocity is negative. So let's do that. So we could pick any values for time in those intervals. Ideally, you pick small positive integers if possible. So we chose t equals 1 for the interval 0 to 2, t equals 3 for the interval 2 to 8, but you could use t equals 4, t equals 5. You could use any value for time in those intervals for your test points. And then the last interval, from 8 to infinity, we're going to choose t equals 9. All right, and all we have to do to pretty much finish answering part C is complete our sign chart and determine on each interval of time if the velocity is positive or negative. You can do that very easily here. Plug in those 3 values for time, 1, 3, and 9, to the velocity, and see if you get a positive or negative output. We'll check in about 30 seconds. All right, so all we have to do is plug in t equals 1, t equals 3, and t equals 9, and we should get positive 21, negative 15, and positive 21. The only thing we care about are the signs, positive or negative. Notice in the sign chart, I put in red the sign of the velocity, positive, negative, positive, and we pretty much have answered our question. When the velocity is positive, the object will be moving to the right. That occurs for times from 0 to 2, and then 8 to infinity. Notice I included within the interval 0 with a square bracket, since that's basically our starting time. Okay, so that tells us when the object is moving to the right, intervals of time from 0 to 2, and then 8 to infinity. When your velocity is negative, the interval of time from 2 to 8, that'll be when the object is moving to the left. Now, when we take a look at part D, here we have our sign chart for the velocity. We're going to need to make a similar sign chart for the acceleration to answer questions when the object is speeding up and when it's slowing down. Let's take a look at that. Our sign charts will tell us when the velocity and acceleration have the same or opposite signs. So let's just kind of make sign charts, which we already did for the velocity. We're going to make a similar one for the acceleration. All right, so I'm just kind of rewriting our sign chart that we created in part C for the velocity. And we're going to make a similar sign chart for the acceleration. Now, I'd like you to try this. Give yourself maybe 2 minutes. Refer back to part A when you had a factored acceleration function. Set the acceleration equal to 0, solve for t, and that will tell us where the acceleration, or at what value for time, the acceleration is 0. You can then make your sign chart, which would then tell you at all other times when the acceleration is positive or negative. Give yourself maybe 2 minutes to create that. We'll check in. It's the key and final step to answering part D. All right, so let's take our acceleration here, which we are using the factored version. If I set that equal to 0, we get a solution for t. The acceleration becomes 0 when t equals 5. So our sign chart's going to look really simple. We just have 2 intervals, 0 to 5, and then 5 to infinity. And if you pick test points, you should get on 0 to 5 that your acceleration is negative, and on the interval 5 to infinity, your acceleration is positive. All the work is pretty much done. We just need to maybe kind of rearrange our work in the sign charts to see when the velocity and acceleration have the same signs or different signs. Let's take a look at all the important values of time, 2, 5, and 8. And let's just split our time interval from 0 to infinity at each of those important values. So we'll get intervals 0 to 2, 2 to 5, 5 to 8, and 8 to infinity. All we need to do is to refer to our sign charts up there to determine on each of those 4 intervals of time if the velocity and acceleration are positive or negative. So if we just fill them in, let's take a look at the first one, the interval of time from 0 to 2. Notice in your velocity sign chart, from 0 to 2, your velocity is positive. And then on your acceleration chart, the interval 0 to 2 is already within the interval 0 to 5. So our acceleration from 0 to 2 will also be negative. So we get here our sign combination on that interval 0 to 2. Velocity is positive, acceleration is negative. And if you refer to your sign charts above, you should get these signs just reading it off your sign chart. And we're pretty much done with this question. Any interval where the velocity and acceleration have the same signs, either both negative or both positive, the object would be speeding up. Any interval where the velocity and acceleration have opposite signs, the object is slowing down. So if we just refer to this table here, which basically comes from our sign charts, we pretty much answer our question and we get our intervals of time here. The object is speeding up from 2 to 5 and then 8 to infinity. And then the object is slowing down from 0 to 2 and from 5 to 8. All right, now that answers example 2, but before we finish this lecture, the work we did in part C and D with creating these sign charts, that answers our current question, example 2, but we will be reusing sign charts for other types of questions later in our course. So make sure you kind of understand how the sign charts were used for parts C and D here, since we will be reusing that later within our course.